Okay, let's dive right into this explainer. I want you to picture something for a second. Imagine flying over this wild, completely untamed river valley, just feeling that raw power of the water carving its way through the landscape below. Well, today we are looking at exactly how a massive engineering marvel comes to life to take that raw current and completely transform it into the electricity that powers our world. It's a pretty stunning journey of engineering, physics, and environmental balance. So let's get into it. Here's our roadmap for today. We're going chronologically, starting with 1, taming the wild river, moving into 2, the giant natural battery, then 3, spinning mechanical into electrical, followed by 4, managing the water supply, and we'll wrap up with 5, the Environmental Balancing Act. All right, kicking things off with Section 1, taming the wild river. Long before the first shovel even hits the dirt, there is this massive hidden effort that has to happen. Teams of engineers and geologists are out there painstakingly studying the valley. They're constantly measuring historical and real-time water flow. They're double-checking the strength of the valley walls, analyzing the soil, and looking way deep into the bedrock layers. And they do all of this for one very good reason, to pick the absolute safest location for the dam. Because frankly, one miscalculation deep in that bedrock, and the entire project is compromised. Once they've finally nailed down the site, the river literally has to be moved out of the way. First, they divert all that water through massive temporary channels. Step 2, they excavate all the way down to unyielding bedrock. Step 3 is pouring millions of tons of mass concrete, or building up a massive earth and rock embankment. And finally, Step 4, they install the dam's internal nervous system, all those tunnels, gates, and spillways. So the site literally transforms from just natural bedrock into this colossal barrier built to hold back millions of tons of water. Moving right along to Section 2, the giant natural battery. Think about what happens as seasonal rain falls and all that mountain snow melts. All that water flows into the river and slowly starts collecting behind our newly built dam. And this reservoir, it acts just like a giant natural battery. By holding billions of gallons of water way up high in a valley, the dam is essentially banking massive amounts of potential energy, just sitting there waiting to be unleashed exactly when we need it. But hey, it's not just a battery for electricity, right? This stored water is a multi-purpose lifeline for the whole region. It's held in reserve for municipal drinking supplies, it keeps farming and agriculture alive during the dry months, and it keeps factory operations running smoothly. It becomes this highly managed resource hub. Which brings us to the really fascinating mechanical part. Section 3, spinning mechanical into electrical. So if you were to look deep inside the dam's thick concrete walls, you'd see water coming through these massive intake gates, passing through screens to block out debris, and then entering what's called a penstock. Now, a penstock is essentially just a hugely thick, steeply angled pipe. And because all that reservoir water is sitting way up high above the turbines, gravity completely takes over. As the water plummets down these pipes, we're talking moving as fast as a car on a highway, it creates immense, crushing physical pressure. Down in the generator room, bam, that highly pressurized water slams right into the turbine blades, spinning them at absolutely incredible speeds. This spinning turbine then turns a connected generator where these massive magnets are rotating past copper coils. That electromagnetic induction converts the mechanical motion directly into electricity. From there, transformers step up the voltage and it gets sent straight to the grid to light up our cities. Now, this whole setup doesn't just run on autopilot. You've got human operators sitting in these high-tech control rooms continuously tweaking the flow. Say the electrical grid gets a huge spike in demand, like on a blistering hot summer day when literally everyone blasts their AC. The operators open the gates wider, letting more water rush through to generate more power. And then, when demand drops at night, they just partially close the gates, saving that water in our natural battery for later. And they definitely aren't doing this blindly. They rely on a vast, interconnected array of sensors feeding them real-time data 24/7. They're watching the exact water level of the reservoir, the intense pressure inside those penstocks, any upstream rainfall that might hit them days later, and even microscopic shifts in the concrete just to guarantee absolute structural safety. It is a highly tuned orchestration of data and mechanics. All right, let's shift gears to Section 4, managing the water supply. So here's a massive engineering hurdle. We've got this giant wall holding back an entire valley of water. But what actually happens when rainfall is historically high and the reservoir literally cannot hold another drop? That's exactly where the spillway comes in. It's the dam's ultimate safety valve. When heavy rain forces the reservoir up to a dangerous level, the extra water gets routed either over a specially designed crest or straight through separate bypass tunnels. This lets the rising water safely bypass the dam entirely in a really controlled way. It completely prevents catastrophic overflowing or structural failure, protecting the integrity of the whole system. But on a normal day, the water management looks a lot different. Operators are carefully routing water through these massive networks of irrigation canals so farmers can actually survive seasonal droughts. At the same time, water is piped directly to treatment facilities to become clean drinking water for expanding cities downstream. The dam essentially acts as the primary distribution hub for the entire region. And we can't ignore the immense human benefit here: flood control. Before a dam gets built, heavy rains upstream can make a river swell so fast it just devastates downstream communities. But once the dam is there, all that sudden excess water is caught in the reservoir and then released gradually over weeks, pretty much entirely mitigating the flood risk. Finally, we have to look at the bigger picture in Section 5, the Environmental Balancing Act. Look, while these structures give us incredible, undeniable benefits, we can't pretend they don't fundamentally alter ancient natural ecosystems. Dropping a giant wall right in the middle of a river completely blocks fish migration routes, and it traps essential, nutrient-rich sediment that would normally flow down to nourish coastal habitats. So, to offset this, modern engineers and environmental scientists are constantly teaming up to build specific engineered mitigations. We're talking complex fish ladders, which are basically water-filled staircases for migrating fish to swim up and over the dam. They also schedule environmental flow releases to mimic natural seasonal floods, and they design specific sediment management systems to pass that trapped mud through. All of this is watched over by dedicated ecological teams. It's a constant, ongoing effort to correct the environmental disruption. Okay, let's bring it all together. A hydroelectric dam is an absolute marvel of interconnected systems. It blocks and stores water, it harnesses gravity to spin out clean electricity, it distributes life-giving water to farms and cities, and it safely manages the absolute worst weather nature can throw at it. It's so easy to look at a dam and just see a giant concrete wall. But as you've seen, it's actually this dynamic, breathing machine connecting the raw power of nature right to our light switches. So I want to leave you with this thought. As we look at this massive system, how can we continue to optimize our engineering to flawlessly balance human progress with essential ecological health? Think on that. Thanks so much for exploring this explainer with me today.